Hi, my name is Bob Zola with Agilent Technologies, and today I'd like to share with you some new equipment that's designed for testing DC to DC converters. What I have in front of me here is a demo board that has a DC to DC converter in the center, and the measurement we're going to make on this DC to DC converter is an efficiency measurement, which is of course very important to have efficient DC to DC converters, because an efficient DC to DC converter means that the device that it's inside of, like a handset or some kind of wireless device, will have a longer runtime off of its battery if the DC to DC converter is efficient. Now normally to do an efficiency test on a DC to DC converter you need quite a bit of test equipment in your R&D lab. So what you'd need is a power supply on the input side of the DC to DC converter to power it up. You need an E-load on the output side of the DC to DC converter, and that would need to be a programmable load that can be swept so you can measure the efficiency at different operating points. And you'd also need a voltmeter or an oscilloscope or a data logger or something that can acquire the data as you're doing that sweep. And you also need to accurately measure current, because the measuring of the current is going to be critical to coming up with an accurate efficiency measurement, and therefore you'd need some current shunts or something like that. Now that test setup is quite complicated. It takes a long time to set up and to get good measurements from. The N6705B DC power analyzer is a single integrated instrument that can make those same measurements much faster setup time and much more accurately, so it simplifies the measurements that you'll be making on a DC to DC converter. Now this is a modular system. We have two modules installed in it, an N6781 battery drain analyzer SMU in channel 1, and similarly an N6781A battery drain analyzer in channel number 2. Now channel number 1 will be connected to the input side of the DC to DC converter, sourcing the power, and channel number 2 will be on the output side of the DC to DC converter, acting as an E-load, absorbing the power. But the critical function of that E-load side is it's going to sweep from low power to high power, so you can actually measure the efficiency across the entire operating range of the DC to DC converter, and that's the measurement that we'll be making. So let me refer you to this block diagram here. What we have is the DC to DC converter. This is a 2.5 volt in, 3.2 volt out, operating at about 1 amp. So the input side is an SMU set to 2.5 volts constant voltage. The output side is the E-load set to 3.2 volts, but it's going to be sweeping the load current from low current of about 0 amps up to full current of 1 amp. And then we'll be plotting the input power versus the output power to measure efficiency. We're going to use some software to do that. It's the 14585 software, and I'm going to bring up that software right now. So on the screen here is a data logger screen. It's a grid, and it's going to sweep. It's going to take 10 seconds to do this sweep, and we're going to see the power in, power out, and a formula, which is another feature of the software. It allows you to do calculations on the traces, and we're going to have a formula that is the efficiency, the ratio of power in to power out, so that we can see the efficiency of the DC to DC converter. Now again, the key to this is going to be sweeping the load, and another function of this software is the ability to generate arbitrary waveforms. That arbitrary waveform is applied to the load side to change the load on the output. So we're going to do a sweep that looks like this. It's going to take 10 seconds. It's going to start at low current and sweep up to high current. Now this looks backwards because it's starting high and going low, but this is a load and everything's negative. So it's going to start at 0 and sweep down to -1, which means pulling full current out of the output side of the DC to DC converter. So what we're going to do now is we're going to start the data logger, and then we're going to start the arbitrary waveform generator. And because this is an integrated instrument, one of the key features is, since they're both in one box, we can cause the data logger to be triggered when you start the arbitrary waveform generator. And normally you'd have separate instruments and you'd have to be pushing buttons on all of them. Because they're integrated, they can work together. So we've already got the instrument all set up. It's pulling current on the load side. It's sourcing power on the source side. I will arm the data logger, and then I will start the arbitrary waveform generator. It's going to take 10 seconds. You'll start to see the traces going by up there, and in a few seconds it'll be done, and I'll be able to describe those traces to you. Okay, fantastic, we're done. So now there's 10 seconds of sweep time across the screen here. Now what I'm showing in these two colors, the top trace, the yellow trace, is the input power starting at 0 power and sweeping up as more power is pulled out of the device under test up to its full output power of a few watts. And the same thing on the output side. This is starting at 0 power, and as the arbitrary waveform generator sweeps, it begins pulling more and more power. And again, because current is negative coming out of the device, it looks like the power is going down, not going up. And here we are at full power here. The pink trace is a formula. It's the ratio of these two. And as you can see, it starts off a little bit down, and then it reaches some peak power right around here. And as you begin pulling more and more power out of the device under test, the efficiency actually goes down. So what this says is this device is most efficient right around here. Now I have markers on the screen. Let me move one of these markers on to see. Right now marker number 2 is saying we're sitting at about 83% efficiency. Right there it's telling us that. But as we start to sweep up into this higher efficiency area, maybe right about here, we're achieving about 93% efficiency. So as an R&D engineer, I can very quickly produce this test. I can sweep through and make measurements across my sweep of efficiency and be able to determine where my most efficient operating point is. And I can do all that in a single integrated package without having to do a lot of setup. Thank you.